And all we're going to do is we're going to review the power rule. Because tonight we'll be needing to use the power rule, so it's better if you kind of remember how to do that before we have to start needing to use it with some other rules combined with it. So remember what your power rule said was to take your derivative, which can be written as dy over dx, or as y prime, whichever way you choose, and I gave all these in y, I didn't do it in the function notation. What you do with your power is you drop your power down in front, keep the number that was just hitchhiking along with you, which is the coefficient of the x cubed, and then you reduce your power by 1. Drop and reduce. Same thing with the next term. Bring your 2 down in front. Keep your 8 right where it is, x, and then 2 minus 1. You reduce your power by 1. Plus, now there's separate rules actually for this 7x and the 5. The derivative of anything to the x power still follows the power rule, though the power right there is 1. So really all you're doing is multiplying by 1 that you don't even need, you know, multiplying by 1 doesn't change anything. So it's going to be 1 times 7x to the 1 minus 1. You're still using your power rule. And then on the last one, you need to remember that the derivative of a constant is always equal to 0. Always. So anytime you have something that there's no variable, it's just a number, its derivative is 0. And I would want to see this step until I'm sure that you've got this part right. Okay? I would actually want to see you write out that whole entire step until I'm comfortable that everybody's figured it out. So if you do show me homework, show me all the steps. And incidentally, only 4 of you have. You need to do the chapter 1 show me the next day or 2, please, so that I can make sure that you're getting it okay. So then this actually now is 3 times 12 is 36. Where'd my x go? Gotta keep my x. 36 times x to the second power. Negative 2 times 8 is minus 16 times x to the first power, and you can write it down or leave it out, whichever one you want, plus 7, and when you have x to the 1 minus 1, that's x to the 0, so it's just 1 and it disappears. And you don't have to write the plus 0 at the end because it doesn't change anything. So this is your derivative, that's y prime. Okay? We're going to do the same thing with the next one, if you want to write it down. Y equals 8x to the third minus 5x squared minus x over 12. But the x over 12 causes a problem for us, so we're going to rewrite x over 12 as 1/12 times x, so that we'll remember that that's really a fractional coefficient. Okay? But everything else works the same. We take the 3, so y prime is 3 times the 8x, and then subtract 1 from the power, minus, bring the power down in front, and we have 2 times 5x to the 2 minus 1 power, minus, the power here is actually a 1, so it doesn't change anything, and we've got 1/12, but since we subtract 1 minus 1, that's going to become x to the 0, and there again, that's just 1. So only the coefficient of the x actually sticks around. So then we simplify by saying 3 times 8 is 24x squared minus 10x, and this one is to the first power, minus 1/12. Okay? Now, if there's anything you don't understand, stop me and I'll go over it again. Next problem is y equals 8 times the square root of x plus 6 times x raised to the 3/4 power. Now that 3/4 power is absolutely no different from using a whole number or anything else. You always just drop the power down in front. But in the square root of x case, we've got a little bit of a problem because we don't have a rule that says what to do with square root of x. So what we do is we change the square root of x into x to the 1/2 power. Anytime you've got a radical, that's always going to be a fraction power. So this is going to be 8 times x to the 1/2 power plus 6x to the 3/4 power. And when we take y prime, it's the 1/2 we're going to drop down in front. And then subtract 1/2 minus 1, plus, bring the 3/4 down in front, and then 3/4 minus 1. So then y prime is going to be 1/2 times 8 is 4, and 1/2 minus 1 is a negative 1/2. Plus 3/4 times 6 is going to be 18 over 4 or 9 over 2. You can use either one. X, and 3/4 minus 1 is negative 1/4. And there's nothing wrong with leaving that just like it is. You don't have to make your powers positive. You don't have to turn them back into radicals. Any questions? This one I can actually handle better if I will rewrite it first as x cubed over x plus 5 over x, which I can then turn around and simplify. X cubed over x is x squared, and 5 over x is the same as 5 times x to the negative 1. So once I've got it in this form, then it's easier to find y prime. Drop the 2 down in front, reduce the 2 by 1, so that's 2 times x to the 2 minus 1, plus, drop the negative 1 down in front, 5x to the negative 1 minus 1, you're always still subtracting 1. So then that means that y prime is going to be See, 2 minus 1 is 1, so that's just going to be 2x. And negative 1 times 5 is minus 5x to the negative 2 power. You don't know how to deal with it in the denominator, no.
What makes it, I mean, because it's still like x to the first power.
It's x to the first, but the power rule only works with, it doesn't work with anything that has the variable in the denominator. Right now, that's the only rule we've got is a power rule. There is something called a quotient rule,
Yeah,
but we're not there yet. So the easiest way to do, and even if we did have a quotient rule, I'll come back and show you at the end of the section when we do the quotient rule. I'll show you how to do that problem using the quotient rule. And
well, it's totally different from that. I didn't
Yeah.
know that you couldn't deal with it in the denominator.
this is the only way we have right now, but by the end of the class, you'll have another way of dealing with it, but it might not actually be as easy as doing it this way. And there's actually another way to deal with the last one, but we haven't learned it yet, so for right now, we're going to deal with it exactly the way we have a rule for it, which is going to be, we're going to multiply it out. So 8x squared is 64x to the fourth. And then 8 times negative 4 is negative 32, which we're going to wind up doubling because there's going to be two negative 32 powers. So that's going to be negative 64x to the third. And then negative 4x times negative 4x is going to be plus 16x squared. So just multiply it out. And then just use your power rule. So y prime is going to be 4 times 64x to the 4 minus 1 minus 3 times 64x to the 3 minus 1 plus 2 times 16x to the 2 minus 1. And the next step is just do the arithmetic then. So y prime is 4 times 64 is 256. X to the 4 minus 1 is 3. Minus 3 times 64 is 192. X to the 3 minus 1 is 2. Plus 2 times 16 is 32. X, because 2 minus 1 is 1. So there's your derivative. Is there any questions over those? Okay. Get the PowerPoint for, somehow I wound up with my 1630 notes still in here. Along with my 1830 notes. And one page. Okay, so this is a new rule. There's a lot of rules in here, but once you practice with them, they should come to you. This one is a little bit more difficult than the 12.1 power rule, but sometimes you can't make everything into a power problem. So sometimes you have to actually cave in and say, okay, I'm gonna use one of these slightly more complicated rules. The product rule is used when what you actually have for your function is itself the product of two different factors. The hardest part about doing the product rule isn't the product rule itself. The product rule itself is actually pretty easy. The hard part of the product rule is recognizing when you've got a product sometimes. So for example here, now since the parentheses are there, it's pretty easy to recognize that that's a product. But if, for example, that product had been written instead as f of x equals 3x squared times 2x plus 3, it's not quite as obvious that's a product. For some people it will be, some it won't be, but that's still a product because you're multiplying something. And the way that we're going to have to find the derivative, even though it's on the PowerPoint, I'm going to do it a little bit differently because I think you'll be able to see it better. You actually have two pieces here, and you have to separate it out into its pieces. So we've got the first factor, and we've also got a second factor. And what happens is we have to take the derivative of each factor. And the derivative of the 3x squared is 6x. And the derivative of 2x plus 3 is just 2. And then the way the rule works is they trade each other's derivatives, and you add them together. So when we find the product rule, what we're going to do is we're going to take, they're using u and v. You can use whatever you want. I'm going to use orange function. Times the derivative of the green function, which is 2. And then I'm going to add to that the green function, which is 2x plus 3, times the derivative of the orange function, which is 6x. And I want to see that step, because if you go wrong, I can tell what you're going wrong on the first step. Okay? So it's first times derivative of the second plus second times derivative of the first. And then you simplify by saying, what is 2 times 3x squared? Well, that's 6x squared. And then what is 6x times 2x plus 3? Well, 6x times 2x is 12x squared plus 3 times 6x is 18x. And since this one is relatively simple, you might want to combine those first two terms. 6 plus 12 is 18. X squared plus 18x. Does anybody have any questions on those? The best way to do the product rule is to separate it out and find your two factors. Take the derivative of each factor and then swap their derivatives and add them together. That's kind of the process that you follow. Now, the best thing about the product rule is that unlike some of the other rules that we're going to have, you can actually check yourself by using one of the other rules. If I took f of x to start with, which was 2x plus 3 times 3x squared, and I went ahead and multiplied that out, 2x times 3x squared is 6x cubed, and 3 times 3x squared is 9x squared, and I took the derivative of this. 3 times 6 is 18, x to the 3 minus 1 is 2, and 9 times 2 is 18. Reduce the power by 1, it's just x. And I can see that I got the same thing by using a different rule.
I can't see the whole problem.
Oh, sorry. So in the beginning, if you're a little bit worried about whether you're doing something right, if it's possible to convert your function into something you can just use the power rule on, because the power rule is actually the easiest one to use. If you can convert it back to where you can use the power rule, you can check your answer. Unfortunately, for finding the derivative of the factor square root of x plus 3 times the factor x squared minus 5x, multiplying it out would get a little ugly, because you have to deal with radicals and fractional powers and all that stuff. So this is one of the cases where you really should be glad you got the power rule, because it's easier to deal with this with the quotient rule. So the only thing we're going to have to do here, though, is because we don't really know how to take square root of x derivatives, and we are going to change that into a power. And that's just so that it'll be easier to actually do the derivatives. And then a lot of times what I'll do is, while I've still got it written like that, I'll just go ahead and write underneath each factor, go ahead and write its derivative. So 1/2 times x to the negative 1/2. And of course the 3, its derivative is 0, so it just disappears. And then x squared minus 5x, its derivative is 2x minus 5. And then I know what I'm going to do is I'm going to multiply those two. And I'm going to multiply those two. They're just trading derivatives, and I'm going to add it together when I do that. So I'm gonna take x to the 1/2 plus 3. And multiply it times 2x minus 5. And then I'm gonna add 1/2 x to the negative 1/2 times x squared minus 5x. And that is y prime. Now, if you want to multiply that out, you can, but you don't have to. Because multiplying it out after that is just algebra. That's not calculus. That's just more algebra work. So you can actually stop at that step. It will. No, it will let you leave it in the, as long as you do all the steps correctly, it'll let you leave it in the first form. And if it ever tells you that's not right, if it actually is an equivalent form, but it wants you to simplify it, it'll say your answer is correct, but it's not simplified. Well, the fact that it's correct is fine with me.
But it doesn't count it right, it counts it wrong.
Even if it counts it wrong, you click that little Ask by Instructor button and I will give you credit for it. Because as long as you've done it right, it's right. Just check them out. Okay, does anybody have any questions on the product rule? Okay, let's go back to my quiz for a second. That's technically a product rule problem. Okay? So keep that handy. We're going to work it again. We're going to use product rule on it. So if we have y equals 8x squared minus 4x quantity squared, we can write that as a product. And then take the derivative of each factor, which of course is going to be the same for each factor. 2 times 8 is 16x minus 4. This one's also going to be 16x minus 4. So I'm going to take the product of these two and add it to the product of these two. So y prime is going to be 8x squared minus 4x times 16x minus 4 plus, same thing again, and then we're going to multiply it out. 8 times 16 should be 128. And that's going to be x cubed. And 4 times 16 is minus 64. X squared, and negative 4 times negative 4 is plus 16x. And since this is going to give me the same thing, I'm just going to add the same thing again to itself. And that's going to give me y prime. So 128 and 128 is 256 x cubed minus, and I think I made an arithmetic mistake the first time I did this, because this is 128 x squared plus 32x. So when I come back and look up here, I think, what did I do? So 3 times 4 is 12, carry the 1, no.
It's this, is it the 64, where we get negative 64x to the third, to the x to the fourth, to get the 3 times the 64?
But 3 times the 64 should give us the same thing we're getting this way. Unless I multiplied wrong down here.
3 times 64 is 192.
Because you got two 32s and then two 64s and all new, all minus.
Time to haul out the calculator.
Well, you should have 4 terms, and I think you only did 3 terms.
Yeah.
Ah, yes, thank you. I only did 3 terms, you're right.
The first and the last.
Because I did this one times this one, and this one times this one,
You didn't do the first and the last.
but I didn't do the first and the last, you're right. And negative 4 times 8 would be negative 32x squared, negative 32x squared, which would be another negative 64x squared, and when I combine those two, I'm going to get the 192. So they do match. We do get the same answer. Okay? Now, as to which one you think is easier, that's entirely up to you. You can do whichever rule you see that it works best for you to do it. I'm not going to tell you which tool to use. I'm just going to give you the problem and tell you to decide which tool you have that you can apply to it. So is everybody okay with those so far? Okay, let's look at the quotient rule. The quotient rule can be a little bit more confusing, as you see looking at the rule there. It's like, they got all these terms. But once you understand the process, it's not that bad. The rule says take the denominator times derivative of the numerator minus numerator times derivative of the denominator and put it all over the denominator squared. And I have students that say this kind of a funny way if I can think exactly how they say it, and it does work. I think they call this ho d high minus high d ho over ho squared. Now, I don't know where the ho came from. And that's kind of a weird way to remember it, but if you can remember that, it's ho d high minus high d ho over ho squared. But I like it dn squared minus nd squared over, or excuse me, dn prime minus nd prime over d squared, because numerator and denominator makes more sense to me. So let's see if we can work through one of these. Okay, what is the numerator? What is the denominator? Numerator is the one on top, 2x minus 1. Denominator is the one on the bottom, 4x plus 3. So we're gonna take the numerator and take its derivative, and the derivative of the numerator is 2. And then the derivative of the denominator is 4. And we're gonna take the denominator times the derivative of the numerator, so that's gonna be 4x plus 3 times 2. And then we're gonna subtract 2x minus 1 times 4. And then put that whole thing over 4x plus 3 squared. So it looks like this.
You go back a slide.
You're welcome. So you need to remember that the denominator was 4x plus 3, and the numerator was 2x minus 1, but its derivative was 2. And then the numerator is 2x minus 1 times the denominator of its derivative, and that was 4, and then just square the denominator. So when you multiply it out, you've got 8x minus 8x, and 6 plus 4 gives you 10, and that's all that's left since the 8x minus 8x cancels out. And your derivative is 10 over 4x plus 3 squared. And unfortunately, there's not usually a good way to rewrite the function if it's a quotient to give you another method to check it. You almost have to use the quotient rule. Now, your next example is a combination of the two rules, and I don't want to jump into combining two rules. If we could just avoid that. And maybe practice on the quotient rule a little bit more first. So again, I'm going to go back to one of the ones off the quiz I gave you. And we'll do it as a quotient rule for a little bit of practice first. So that was a quotient rule problem. Y equals x cubed plus 5 all over x. So we're going to treat it like a quotient rather than use the trick to make it into a power rule problem. We're going to actually just treat it like a quotient. So the numerator is x cubed plus 5, and the derivative of the numerator, n prime, is 3x squared. And the denominator, which I just call d, is x, and d prime, the derivative of x, is just 1. And then I'm going to put the denominator in the, I go ahead and start out as my first step. I put my denominator squared in the denominator for my derivative. And then I go back and I take my denominator, which is x, and I multiply it times the derivative of the numerator, which is 3x squared. And remember that I'm subtracting Product rule is add, but quotient rule is subtract. And I'm going to take the numerator and multiply it by the derivative of the denominator, which is just 1. So then x times 3x squared is 3x cubed minus x cubed plus 5 over x squared, and 3x cubed minus x cubed is 2x cubed plus 5 over x squared. And admittedly, this doesn't look much like what we got last time, because what we got by doing the power rule looked like this. But those two really are equivalent expressions. They are the same. Because if you break this up, then you see that x squared takes away that and makes it x to the first, and if you move x squared to the numerator, you get 2x minus 5x to the negative 2 power. So those really are the same expression, they just look different. Hmm?
One's plus and one's minus, like
Oh, it matters because I copied something down wrong. I just realized I did that. If I pull this back over here, let's see.
see, that's what,
You go back and see where I goofed up on one or the other, so we're gonna have to figure out which one I goofed up on. I goofed up on this one. Because when I do minus times x cubed, I got minus x cubed, but I forgot to multiply the minus times the 5. So that would be minus 5 and minus 5, which would make that minus 5, which is what it should be. So I'm glad you caught that. Be careful about distributing, because I do it, I know no better than y'all are. I'll forget to get that second term with that negative sign sometimes, so got to kind of watch out for that. Okay, before we go on, I'm going to make one up and ask you to work it, because again, that next problem is a little bit of a doozy when we start mixing them up, and I know that. So I always try to come up with a few extra ones that are not in your notes. So let's see, we want another quotient rule problem. Do that one for me. X squared minus 81 over x minus 9, and use your quotient rule. So who can tell me the derivative of the numerator?
2x.
Okay. What about the denominator? Just 1. What goes in the denominator of the derivative? Okay. What about the numerator? Okay, so that's x minus 9 times 2x, which is x squared minus 81, which is just 1 and doesn't change anything. That's right. So 2x times x is 2x squared, and minus 9 times 2x is minus 18x, minus x squared minus, plus, thank you, plus 81 over x minus 9 squared. And then my 2x squared minus my x squared will give me x squared minus 18x plus 81 over x minus 9 squared.
Does that matter? I mean, because it's the same thing, it's like 1, because the top is x
Yeah.
minus 9 squared.
Yeah. Yes, it does, and I'm glad you brought it up instead of me having to bring it up, because I'm going to show you what we could have done back up here. So yes, the numerator does factor to x minus 9 and x minus 9 over x minus 9 times x minus 9, which is 1. So the derivative of that is 1, right? Seems like an awful lot of work to go to for 1. Let's come back up here to the original derivative though. The original function, not the derivative. The original function would have factored also, right?
But it would have just taken 1.
It would have, and that's why I want to look at it. So x minus 9 times x plus 9. The x minus 9s would cancel, so my original function was just x plus 9, as long as I didn't let x be 9, right?
It would be 1.
And your derivative would have been 1. So is algebra totally useless? No, if you use it in the right place, it can be really handy. Because you have to admit, that was an awful lot easier than that. Okay? So now we're ready for a challenge, right? Now we're ready to do a product and quotient rule at the same time. And I'm not going to go through it with you on the PowerPoint. I'm going to work through it with you step by step, because this one can get tricky. So we're going to have to set this one up in steps. So there's our original problem, which you got on your paper. We want to take the derivative of 3 minus 4x times 5x plus 1 in the numerator over 7x minus 9 in the denominator. And the numerator in this case is a product, so when we have to get the derivative of the numerator, we're going to have to use product rule. So the first thing I'm going to do is I'm going to write down some steps for myself here. The numerator is 3 minus 4x times 5x plus 1. And when I do the numerator and get its derivative, what I've got to do is I've got to make these two factors trade their derivatives. So the derivative of this first part here is -4. And the derivative of the second part is 5. So what I'm going to do is I'm going to take the 5 and multiply it times the 3 minus 4x. And then I'm going to take the -4 and I'm going to multiply it times 5x plus 1, and I'm going to add them together. So 5 times 3 is 15 minus 20x, and then minus 4 times 5 is minus 20x, and minus 4 times 1 is minus 4. And 15 minus 4 is 11 minus 40x. And while normally I wouldn't care if you simplified your derivatives at all, in this case it's going to make your life easier. Because you really would much rather use this in the quotient rule than you would have to use that, even though it would be correct. So now we're going to look at the denominator. The denominator is 7x minus 9. And fortunately, it has an easy derivative, which is just 7. Whoa. It's set up to go to sleep too quickly. So then what we're going to do to actually get the derivative of this thing, now we're ready to do a quotient rule, right? So the quotient rule says take your denominator, 7x minus 9, and square it. And then take your denominator again, 7x minus 9, and multiply it by the derivative of the numerator, which is 11 minus 40x.
You don't take the derivative of that, the 11 minus 40x.
No, because that is a derivative. That's the derivative of your numerator. Okay? And then we're going to subtract the numerator, which I'm going to slide this over so we can see it all. We're going to take the numerator, which is the 3 minus 4x times 5x plus 1, and multiply it times the derivative of the denominator, which fortunately is just 7. So this is your y prime, or the way the textbook has listed it out is d over dx, but you can call it whatever you want to. I think it's d sub x. So there's your derivative. And actually, if you type that in My Math Lab, it should take that. If that was a question from My Math Lab, it should take that answer just like that, ugly though it is. But if you want to clean it up any, you just multiply these out. 7x minus times 11 is 77x minus 99 minus 280x squared minus 360x And then I'm gonna do this one up here because I think I could make too many mistakes if I didn't. So 3 times 5 is 15x minus 20x squared plus 1 minus 4x. And then minus 4x of 15x is 11x. And then I'm multiplying this whole thing by -7. So that's going to be -7 times 11 is negative 77x. -7 times -20x squared is going to be positive 140x squared. And -7 times 1 is going to be -7. So that drops out. Let's kind of put these terms in the right order. This is going to be positive 140x squared, to take care of those two, minus 360x, and minus 106. And there's your numerator, all over 7x minus 9 squared. So that does look a little bit better. You might be able to factor the numerator and factor out something from the denominator, I don't know. But I think that answer looks just fine. And there again, my math lab should take that. Yes.
Was it not negative 140?
Excuse me?
Was it not negative 140?
Oh, it is negative 140, thank you. It is. Because the negative 280 got to be boss. So that should be a negative 140. Any other questions or any other arithmetic mistake you're going to catch me in? Okay. Now, why would we even need such things in business? You know, where does all this lead to? Well, if you follow your notes, we're going to talk about something called average cost. And while I'm switching back, average cost. I think most of y'all have had statistics at this point. Even if not, you've probably read enough to know what an average is. Average is the sum of all of them divided by how many? Does that make sense? Average cost would be the total cost for X units divided by whatever number of units X actually is. So when we do cost functions, you need to find average cost, then you divide the cost function by X, which is, of course, a product. Or, I'm sorry, a quotient, not a product. And by the same idea, then your average revenue per item is going to be revenue divided by how many items, or profit divided by how many items, to find the average function. The marginal average function is the derivative of the average function. But you have to remember to divide the original function by X first to get your average function. So the rate of change of average cost is called the marginal average cost, and it's the derivative of the average cost. and its symbol is C prime of X. Marginal revenue, R prime of X, is the derivative of the average revenue function, which is R of X over X. And the marginal average profit function is the derivative of the average profit function, P of X over X. And if you think about it, a company's going to be interested in making the average cost as small as possible, because if you make your average cost as small as possible, then hopefully that leaves you with more money. You want to spend less per item and still be able to charge a good price. So you're going to want to minimize that average cost. And we can usually use the quotient rule to find this derivative, although it is possible you could use the product rule and just make your X in the bottom have a -1 power. So let's look at a situation. The cost in dollars for manufacturing X 100 small motors, be sure you notice your units, for X 100 small motors is given by this cost function. Now, this is not the average cost function. This is the cost function. It's how much it costs to make X 100 small motors. If I want to know the charge per motor, then I have to divide that by X. Because that X, remember, is going to be in hundreds, and I can divide the result of that by 100 if I want to take it down to a single motor. But they want us to find the average cost per 100 motors. And the way that you find that is you just put your C of X function over X. And since your C of X function is already quotient, the easiest way to put that over X is actually multiply it by 1 over X rather than divide it by X. Change it into the cost function times 1 over X. And so for that reason, it turns out to be 3x squared plus 120 over 2 times x is 2x squared plus 1 times x is x. So now this is your average cost function. It always has to be your first step to get the average cost function if you're going to talk about marginal average cost. Does anybody have any questions about how I got the average cost function? Just remember that dividing that function by x is the same as multiplying it by 1 over x. Because ultimately you wind up multiplying through the denominator of the cost function by x. Okay, at this point we're going to find the marginal average cost. So I'm going to switch back over here and work it out by hand because I think that might be easier. So remember our average cost function if I divide that by x, then we're going to be timesing it by 1 over x. So my function winds up looking like this. And it is a quotient by x plus x plus x. And now I need to take the derivative because I'm looking for marginal average cost. Every time you hear the word marginal, your mind should go to slope, rate of change, or derivative. because that's what marginal means. And in order to take the marginal average cost, I'm going to need two derivatives, which I'm going to slide over here and go ahead and take them. The derivative of the numerator, which I'm going to call n prime, is going to be 6x, and the derivative of the denominator, which I'm going to call d prime, is going to be 4x plus 1. So when I do my derivative, C average prime, since it's a quotient, I'm going to take the denominator, 2x squared plus x. I'm going to put it in the denominator and square it. Then I'm going to take that same denominator, 2x squared plus x, and I'm going to multiply it times the derivative of the numerator, which is 6x. Then I'm going to subtract the numerator, which is 3x squared plus 120. And I'm going to multiply it by the derivative of the denominator, which was 4x plus 1. And that is your marginal average cost. And since it's marginal, it's going to be in dollars per X hundred motors. Oh yeah. And you can simplify the top one. I didn't yet, because part C says, we're going to see it in the next chapter, average cost is generally minimized when the marginal average cost is equal to 0. Find the level of production that minimizes your average cost. Well, what you want to do is you want to take C prime of x and set it equal to 0. And it probably would be easier to go ahead and say 6x times 2x squared is 12x cubed plus 6x squared minus, and 3 times 4 is 12x squared, cubed, not squared, cubed, plus 4 times 120 is 480x. 1 times 3x squared is 3x squared. And 120 times 1 is 120. And then when I subtract all of that, what I'm actually going to get is minus 12x cubed. I'm going to go ahead and take the minus times the squared term and get minus 3x squared. And minus 480x, and minus 120. And that's all over the denominator still. But since I can combine some like terms, I'm going to go ahead and try to combine the ones that I can. Because I see here that I've got 12x cubed and minus 12x cubed that will cause those to drop out. And then I've got minus 6x squared and plus 6x squared minus 3x squared leaves me with 3x squared minus 480x minus 120 over 2x squared plus x. And I need to set that equal to 0. And the only way that's going to be equal to 0 is going to be if my numerator is equal to 0. It doesn't matter what the denominator is, as long as the numerator would be equal to 0.
So the denominator's still squared.
Yes. I'm kind of, I guess, tending to dismiss it at this point because it doesn't really have any bearing on what we get here. Okay? So really, if this is only true if the numerator is equal to 0, then that's what we want to solve for. Now, there's 2 or 3 different ways we could go about solving it at this point. We could factor it and hope it factors, and in fact it probably does factor, because I know I can factor out a 3. But I don't know that I particularly want to factor x squared minus 160x minus 40, since factoring is not my favorite activity. So at this point, unless you just want to factor it, you have 2 options. You could do quadratic formula. A is equal to 1, B is equal to negative 160, C is equal to negative 40. Just plug into the quadratic formula. I'm going to leave that up to y'all. I'm going to go to the graphing calculator, and I'm going to plug in, since the 3 really doesn't matter, I'm going to plug in the x squared minus 160x minus 40, because that's the only thing that really needs to be equal to 0. That's one too many ones there. So I'm going to enter that in at y1. And I'm going to go on a window where, really, it's not going to be negative. You can't have negative 100 motors. So we're going to start it at 0. And the original problem, if you look at it, says that really this cost function only applies from 10 to 200, so there's really no point in looking at anything less than 10. And I'm going to let it count by tens, but then after I set up the domain that it gave me for the problem, then I'm going to go zoom and choose fit, which is zoom 0. And what I'm looking for is that value right there. I'm looking for where it has a 0. And I can find that by going to second trace to go to calc and choose the 0 option and move my cursor to where it is before the 0 and then after the 0, and make sure those 2 little things point at each other, and hit enter, and it says that happens at 160. Now, if you were actually gonna use the quadratic formula, you would have come up with, let's see, the opposite of 160 is, a negative 160 is 160, plus or minus the square root of negative 160 squared minus 4 times 1 times negative 40 over 2 times 1. Let's see. That looks a little strange. Let me make sure that it didn't make any difference if I didn't put parentheses in there. Nope, that's right. So we're gonna hope that you can take a square root of that.
Not even. It's 164.
And 160.5.
Yeah, that's what I got.
Okay, now that actually does work though. Because if x is equal to 160 plus or minus 160.5, then x is equal to, if you add these two, you get 320.5. Over 2. But if you subtract them, you're actually going to wind up with negative 0.5 over 2, which doesn't make any sense because you can't have a negative answer. So you toss that one out. But 320.5 over 2 is 160.25. This might be a good time for a break. Let me double check all my arithmetic. So let's leave it there for a while and let me look at this.